Start referencing. Be like, okay, I've seen that benzene can go from this to this. How do I do it? Okay, great. Now that we're here, there's another reaction. I'm not going to tell you where this is, but convert this into the following. First off, what do I say? Identify what's changing. What is changing? Okay, so replacing an H. We're losing an H and replacing it with what? This weird looking structure. Okay, let's draw this as a diagram. This would literally look like, I'm just going to do, this is equal to NHC double bond O CH3. Okay, we're starting to visualize things a little bit easier. Piece things like a puzzle. We took apart one hydrogen. And then what do? We added this CH3 group, or this carbonyl ketone weird hybrid. Now use your memory, try to recall, where have I seen this before? There's only one slide. There's only one slide where you see this before. It's in the same chapter. It's using what? Okay, so it's symmetrical. The molecule is symmetrical. Okay, how do we know this? Practice. I know I dove headfirst into a question that required you to have revised, but my point being, I want to show you the steps to approaching these questions so that when you go revise and you do read through the content, you can at least you can at least have the skills ready to approach solving these problems before your exam. Okay. We're adding this group here, this weird looking group. The reaction that we're looking for is adding acetic anhydride as a protecting group. Those reactions. We're adding an acetic anhydride protecting group. Abdelhamid, how am I going to know what acetic anhydride looks like? Acetic acid, vinegar, yum. Looks like this. CH3, C double bond O, OH. Acetic anhydride is this structure. Oh, wait, I'm running a bit small. People online, can you see what I just drew? So this is acetic acid. Acetic anhydride is exactly this structure minus the hydrogen duplicated on itself. So let's draw that. C of 1O, CH3. So if you ever forget what acetic anhydride looks like, okay, remember acetic acid, Abdelhamid said vinegar. He did that weird noise with his mouth. Okay, now we know that. We just have to remember what acetic acid looks like. It's basically this group here with an OH. We duplicate it on itself. We have acetic anhydride. This is acetic anhydride. Okay, well, we're starting to see something. Okay, I see my C double bond OCH3 here twice. Now, all I need to do is have this in solution with this, and this reaction proceeds. Issue is that this mechanism isn't listed. But the mechanism is pretty simple. I'm going to erase part of the board so I can draw the mechanism. Did you guys take a photo of this? Oh, well, we needed that. Oops. NH2. So we're trying to protect our NH2 group. Let's do that. We have NH2. Also, when I draw this circle here versus these double bonds, it just means resonance. I'm just lazy and I don't want to draw it. Not me. Chemists made this. And we're turning it into same thing, except now we have COCH3, or we said is C double bond O CH3. Okay? And we successfully identified that. We said, oh, it's going to be acetic anhydride that we're adding. CH3, C double bond O, CH, no, C double bond O, CH3. Okay. What's happening? What attacks what? Step one, move left to right on both your starting and final compounds. Identify what's changing. Left to right. Is the ring changing? No. Is the NH2 changing? Yes. what on the NH2 is changing? We're removing one hydrogen, so right off to the side, loss of one hydrogen on NH2. If you want to keep a checklist for yourself, do that. And then what? 2, we're adding that weird group, adding C double bond O, CH3 to NH2. So these 2 things need to happen for us to get here. So let's start doing that. On NH2, what do we have? We have lone pairs. These lone pairs, what did I say about lone pairs earlier? Lone pairs can be exchanged readily if enough incentive is given for the molecules. Okay. We want to donate these lone pairs somehow, such that we end up with C double bond O, CH3. What's the most susceptible molecule in solution? Well, we look above and below the arrow. We have our acetic anhydride. Don't have anything else in solution. The most susceptible bond to go to where we want is to attack this carbon. Why not this carbon, Abdelhamid? It's the same thing, because remember, they're symmetrical. If we attack this carbon, I'll explain why that carbon in a second. If we attack this carbon, carbon can have how many bonds? 4. If carbon has 5, hellfire. Thank you. Good. We're getting there. If carbon has 5, hellfire, that means something needs to break. What is the most susceptible bond that's going to break? This one. It'll break here. If you forget that it's the most susceptible bond, always just look to your structure. Is there an O here? No. So that means we only want this part of the molecule. We really only want this part. Rip it off, attach it to our NH2, remove a hydrogen. So if we redraw everything, we've drawn the mechanism. It's just one step, really. We have what? Our ring, left to right. Ring isn't changing. We then have NH2. I'll get there in a second. NH2. Okay. Then we have what? We have C double bond O, CH3. Okay, yay, we did it. We ever decide? No, we don't actually. There's a NH2. NH. What has to go? A hydrogen. But before that, redraw this structure here, and I'll explain why in just a minute. When electrons fall onto oxygen, it becomes minus. Remember what I said? If I give you a pair of electrons, your charge becomes negative. So let's do that. Left to right, we have O minus C double bond O, CH3. Okay, if we have a minus here, we need to have a plus somewhere to balance everything out. How do I know this? It's neutral up here, 0 overall charge. Therefore, we need to have a 0 overall charge here. Where is the plus going to go? How do we know it's nitrogen? It has more bonds than we usually see it has. Same thing with, remember what we said with oxygen when we were looking at PBr3, converting the alcohol to an alkyl bromide? We said that if oxygen has 3 bonds, it has a charge of plus. If nitrogen has 4, it has a charge of plus. Trust me, with time, this stuff will basically become ingrained in your brain, and you won't be as panicky and like have to think for a minute. It just becomes second nature. So we have a plus here. We have these hydrogens. Let's just redraw them such that it's a little bit more easier for us to visualize. Plus. Okay. Well, we need to get rid of one of these hydrogens. How are we going to get rid of one of these hydrogens? Well, the only thing really in solution at this moment is something with a negative on it that wants to stabilize itself. The fact that it has a negative, it's freaking out. It's like, I got to take something. I have to be stable. Right now, I'm not stable. We have a molecule that's in solution that's like, I have a hydrogen, take it. I don't like having a plus. Take it. So they agree to exchange. This exchange happens. So this lone pair of electrons will attack the hydrogen, taking the hydrogen. We break this bond, and the electrons fall towards nitrogen. If we redraw everything, we end up with this structure. And and we end up with acetic acid, basically, which is HO, C double bond O, CH3. But really, in organic chemistry, we don't care about side products, which is why in a lot of mechanism reactions moving forward, in chapter 16, A, B, 17, whatnot, you'll start with stuff, and then you'll not end up with the same stuff because we don't care about the side products. They're either boiled off, evaporated, filtered. We don't care. We're interested in the major organic product. Questions about what I just said, if I move too quickly? Good?